Hello and welcome to another power system analysis class. Today we're going to cover economic dispatch, one of the most important and practical topics in power system operations. We spoke a little bit about economic dispatch in the previous class. We want to uh, dive deep into that. And by the end of today, you should understand the mathematical formulation of the economic dispatch if we reach that part. Um, and Also, we will solve some problems on using both a direct method and an iterative method called as the lambda iteration. So let's get started with today's class. So the first thing is, why do we need to think about dispatch at all? So the load on a power system is always variable. It changes hour by hour, minute by minute, but the total generation capacity installed in a system is almost always greater than the actual load at any given time. Obviously, if we have less generation than load, we're going to have shortages and blackouts. So to have a reliable grid, we always need to have more generations than load. So that means at any instant, we have more generation available than we actually need. And the question becomes that which generation do we use and how much do we ask each one to produce? Obviously, not all generators are equal. Some are renewable energy. They require less maintenance and they don't require fuel, so they are cheaper to run. And some are gas or small generators, which are more expensive to run. And we want to maximize the final goal for electric company is to maximize its profit. And the way to maximize its profit is to use the cheapest source as much as possible. But there are limitations for that, obviously, and I'll explain about that. Now, for generators with zero or non-zero fuel costs, like the wind and solar, as mentioned, the answer is very simple. Use all of it. It's use it or lose it. Very common term that we have. So for a wind turbine, obviously we don't have storage. A lot of storage is very expensive, so you would lose it or use it or lose it. If the wind is blowing and you don't capture the energy, it's wasted. And it's the same for solar as well. For a hydroelectric, it's more complex. You have a limited water supply for the year, so you have to be strategic about when you use it. You can't just open the dams. And for fossil fuel plants, there are startup and shutdown times that can take many hours. So you can't just flip them on and off instantly. And I've already mentioned a little bit about that. So economic dispatch is specifically about the instantaneous problem. Given the current load, what is the cheapest way to dispatch the generators that are already online and available? Now, we spoke about this graph previously, but I just want to reiterate that traditionally utilities classified their generators into three broad groups based on how they are used. First, we have the baseline or baseload units. These are large coal and nuclear plants. They are designed to run continuously at or near their maximum output. They are the most efficient at full load and have very high startup costs. So you almost never shut them down unless you have like a maintenance every year or every few years. Second, we have the mid-load units. These are smaller coal plants and gas plants that they cycle on and off daily. They ramp up during the day when demand is higher and ramp down at night. Then third, we have the peak units. These are typically combustion turbines, often running on natural gas. And the reason that we use natural gas because it's much easier to run and start compared to coal. It takes a few hours, sometimes 3-4 hours to just get it started. Um, and They are only needed for a few hours a day, or even few days a year. And they are just turned on during the periods of peak demand. So think of a hot summer afternoon when everyone's air conditioner is turned on, and we have an unusual hot summer, and we don't have enough generation, so we turn on these peak units. They are less efficient, but they are fast. That's the reason these are the most expensive option out there. But now the problem is that the picture is changing rapidly in the recent decades with solar and wind and renewable energies. Their output is variable and depends on weather conditions. Typically, we operate them at whatever maximum power is available, and we don't curtail them unless absolutely necessary, because again, it's the cheapest form. The bar chart on this slide shows the trend in new capacity additions in the US. You can see the dramatic growth in wind and solar as well. And that's when we get to this slide. This slide shows a chart of utility scale generators and their capacity. The capacity additions in the United States over recent years. And if you look at the trend here, in earlier decades, new capacity additions were dominated by coal and other sorts of, you can see like coal, hydro, natural gas, petroleum. So fossil fuel dominated the chart in the early days. But in the recent years, it has shifted. Now, you can see that coal is mainly replaced by natural gas in the 2000s. And the share of renewables like wind and solar has significantly increased in the past decade. So the vast majority of new capacity being added to the grid is now from wind and solar. The reason that we have shifted from coal to gas is because gas has become much cheaper because of the shale and the fracking revolution, and also because of environmental concerns on carbon dioxide and greenhouse emissions. For natural gas, it's much cleaner and less greenhouse emissions compared to coal, and it requires less filtration. I'll explain how the filtrations work in, for example, a coal power plant. Now, economic dispatch algorithms and the supporting market structures have had to evolve to handle this new reality that we have shifted from fossil fuels to renewable energy. Now, this slide shows the breakdown of actual electricity generation in the US by fuel type. You can see this is from 2010 to and the projection to 2050s. Notice that in the first half, you can see that from 2010 to 2020, natural gas has increased rapidly. Coal has shrinked. You can see the difference here. And renewable energy has also gained traction. And it's now at around 21% of the total energy supplied to the grid is renewable energy. And in 2024, wind accounted for 10.2% of the total renewable energy generation, total grid generation. So about 50% of all renewables is wind, and solar was around 3.9%. Now, the reason renewable share of generation is lower than their share of capacity is their capacity factor here. Wind and solar don't produce at their full rated capacity at all times. A wind turbine might only produce at around 30 to 40% of its maximum on average, because we have windy days and calm days and also cloudy days and sunny days. So, and then you can see that natural gas has largely displaced coal as dominant fossil fuel. And the reason is, again, green gas emissions and carbon emissions, and also the fuel cost actually plays a higher role as well. Now, this map shows where wind power plants are located across the United States. I think you're already familiar with this. The bigger the circle, it means it's higher, capacity. You can see that wind resources are heavily concentrated in the middle of the country, the Midwest. It's the wind tunnel of the country. The Great Plains, stretching from Texas, especially the Texas Panhandle, up through the Dakotas, North and South Dakota. This region has some of the best wind resources in the world. Notice the areas with the best wind resource are not necessary. So this is the areas that we have the best wind, but they are not necessarily close to the major population centers. So the major population centers are going to be around the coasts, like here and here, here and here. And these account for like 70% of all US total population. So you can see that we produce energy where we don't need it that much. So what can we do? We have to transmit this to the population centers. This part is actually a little closer because of to Chicago, but here you can see that in Midwest and in Great Plains, we generate a lot of wind, but we can't use it. The only way is to transmit them in high power transmission lines, and that is very, very costly. So again, because of the large cities which are on the coasts, and they consume an enormous amount of power, they have no wind. Offshore wind is solving that problem, but again, it creates a transmission challenge. We need long distance high voltage transmission lines to move power from where it is generated to where it's consumed. Now, on the map, if you spot West Texas, where we are, it's actually sitting on one of the best wind resources areas in the country. You can see it's a concentration, a lot of wind turbines. We have very good winds, like we call class 3 best winds, and very good actually solar radiation as well. So it's a very good area for both wind and solar. But again, there is not a lot of population that could be used. And that's the reason there are a lot of interest in these big data centers to put a data center companies and AI companies like Meta, Google, and Amazon, Microsoft, OpenAI, Anthropic, to put their data centers in these areas, because you just need a lot of power, and there's not necessarily a need of big cities. You have a fiber optic, you can just connect it to the internet, and you're able to run it. I think there are some plans to put one between Amarillo and Lubbock, and they're working on that. It's going to be one of the largest, but there are some resistance because of the use of groundwater. Problem is water. They consume a lot of water for cooling, and there's not a lot here. So there are some environmental concerns over there. Now, the challenges of wind dispatch. This slide here illustrates one of the fundamental challenges we have with wind power, and it's the variability of wind power. The image shows actual wind output for California over the course of a month. It's powered by hour and by day. And you can see that the output fluctuates significantly, both within a single day and from one day to the next. You can say from like day 29, then day 26, day 25. You can see how it fluctuates in different hours during morning, afternoon, and so on. And this variability actually makes the economic dispatch more challenging for these. With a conventional thermal plant, if you tell it to produce 200 megawatts, it will produce 200 megawatts. But with wind, it doesn't work that way. We get whatever wind that it's given to us, so we can't predict it. It's going to be very difficult to predict. Now, this means the rest of the dispatchable generation on the system needs to constantly adjust their output to compensate for wind fluctuations, on top of responding to changes in load. Now, this is one reason why grid operators and researchers are very interested in energy storage and demand response tools that can help absorb or smooth out these fluctuations. And energy storage has become a very important topic, especially with the rise of renewables. Now, the two dominant types of large-scale generations, we have thermal versus hydro generations. But these one historically, the most dominant one has been thermal units, which burn fuel to produce heat, which drives turbines, and hydro units are also used. But the problem with hydro units, we have some limitations. Now, the hydro units use falling water to drive turbines, but again, we have limitations. You don't have infinite amount of rivers. We have limited amount, and we already have dammed all of them. The one that we can use, or that are close to centers, and environmentally you can do it. We've already used them. Sometimes you may think this is a good river and it's like a good valley or a canyon. Why don't we dam it? Sometimes there are environmental impacts. Sometimes the soil must, like for example, some areas soil is salty. So if you dam the river and the water backs up, the water becomes salty, and then you can't use it downstream for agriculture or something like that. So there's a lot of consideration when you're building a dam. Now, for hydro, the fuel is water. It's essentially free. That's great. But there are many operational constraints. You have a limited amount of water available, first of all, and often on seasonal basis, you have to manage reservoir levels for flood control, recreation, and water supply. You have to maintain minimum downstream flows rates for fish migration and navigation as well, and also agriculture. Because of these complex long-term constraints, hydro optimization is typically done over months or even years. It is much more of a planning problem than a real-time dispatch problem. And now, in this course, we are going to focus on the thermal units and some wind, and we will look at short-term real-time optimization, which is the economic dispatch. The other thing is that wind is rapidly growing and is increasingly part of the dispatch picture, which is why we will mention it alongside thermal a lot. Now, this slide shows a block diagram of a thermal generating unit. The basic idea is very simple. It hasn't changed for 100 years. Fuel, whichever it's coal, natural gas, or nuclear, is used to produce heat. That heat converts water into high-pressure steam. The steam drives a turbine, which spins a generator, which produces electricity. Now, an important concept here is auxiliary power. Not all the electricity generated in the plant can be sent to the grid. Some of it, typically around 2 to 6% of what we call a gross output, is used within the plant itself. and it's used to power pumps, fans, control systems, lights, anything that is powering the plant itself. And the power that actually leaves the plant and is delivered to the grid is called the net power output, and that is the power that we use in our cost models and economic dispatch models. So we always work with the net power output, not the gross power output. And that's the actual power that we are selling. But we have to put that loss, that's a power loss, into account when you're, calculating the cost. Now this slide shows a diagram of a modern coal-fired power plants. Now you can see the full process. Coal is burned. First they crush it and then they burn it in a boiler to produce steam. The steam drives the turbine. You can see step by step, and you can read faster than I can. And the generator, and then the steam is cooled in a condenser and recycled back to the boiler. If you have been to, I don't know, Exo power plant, I think they have converted it now to gas, but you can see all the steps, the boiler, the condenser, everything. The boiler is actually on the 4th floor, the upper floor. And when you go down, you can see the generator on the 1st floor. Now, the modern coal power plants include elaborate environmental control systems, like scrubbers to remove sulfur dioxide, electrostatic precipitators to capture particulate matter. And what they do, and let me give you an example. So that the gas that it's getting out of the system, it goes usually through imagine that you have a metal plate, and that metal plate, you're giving it a negative charge. Okay, so you have negative charge on all of these. So imagine you have a mesh, and you have this mesh has negative charge, and all the fumes and gas coming from the exhaust is passing through this. Okay, the exhaust from the power plant. Now what happens, these particles, they usually have positive charge, and when they reach this negative charge, they're gonna stick to it. Okay, so all of these, it's gonna be like a black powder dust, sticks to this plate, and what they do, they have these big hammers. Imagine that you have like a big hammer, and you hammer this, and what happens, all these dusts drop down in a bucket, imagine, and then you discard that bucket. And usually what they do, they use it for making asphalt, for example. So this is one, and then you have catalysts and different filters that it goes through, and eventually the only thing that comes out is just carbon dioxide. So still it's a lot of carbon, but you are getting rid of sulfur, nitrogen, and so on. And this part is actually an expensive part, and it's the same thing as a car exhaust and catalyst, but in a huge scale. And one thing to keep in mind is that the efficiency of these modern coal plants, which is the fraction of the fuel, energy, and content that is converted to electricity, is typically in the range of 35 to 40%. So the maximum efficiency that these plants have is around 35 to 40%. So 60% of the power or the energy is wasted in the system. Now, this slide shows the turbine hull of a nuclear power plant. You can see how huge it is. Now, nuclear plants work on essentially the same thermodynamic principle as a coal or a natural gas plants. Heat is used to generate steam, and the steam drives a turbine. The difference is that the heat comes from nuclear fusion rather than burning fuel. Nuclear plants are baseload units. They are very expensive to build, but the fuel cost is relatively low. They run best at constant full power output around the clock, and their large physical size and long startup times. It requires days to bring a nuclear unit from cold shutdown to full power. They are almost never used to follow load variation because it takes days to turn on and turn off. And so that for these reasons, in the context of economic dispatch, nuclear units are typically treated as must-run units, what we call. They operate at their maximum output, with their output simply subtracted from the total load before the dispatch problem is solved for the remaining generator. So we have that as base load, and we solve it for the rest of it. Now, this slide shows a basic gas turbine, also known as a combustion turbine. It's very similar to a jet engine. So you have compressed air, and then you have, which are fans and pump, and then you have fuel added to it, and you have the combustion chamber, and you have the turbine and the exhaust. And you can see the differences in the temperature. Temperature going into the turbine is 1100 degrees Celsius, and the one coming out is 550 degrees Celsius. So the exhausted gases are around 67%, and the AC power generated 33%. So the efficiency is around 30%, 33%. And from that 33%, 2 to 6% is again consumed in the power plant itself for the compressors and pumps and so on. Now, you can see that the maximum efficiency here, the typical efficiency here was around 30 to 35%. But if you want to measure the maximum efficiency, for this case, it's going to be around 42%. Now, this is called a simple cycle. And I'll show you another type as well. So this is called a simple cycle power plant or gas turbine. They are not very efficient. The efficiency is around 30% to 35% efficiency, which is pretty low. Now, that means roughly 2/3 of the fuel energy goes out the exhaust stack as a waste heat. Now, this heat is pretty high. It's 550 degrees Celsius. The boiling point of water, how much is that? 100 degrees Celsius. So another type of system that we can use is to have this exhaust, divert it to a steamer, use it to evaporate or steam water, and put that through another turbine and generate electricity from the wasted heat. You can see it here. And this is called a combined cycle power plant. These power plants have 2 generators. One is directly connected to the gas turbine, which essentially it's something like a jet engine, but different because these work nonstop. And then the exhaust gas is directed to a heat recovery steam generator. It generates heat, and the steam goes through a steam turbine, and the steam goes to a condenser and then becomes water, and it's pumped back. The only drawback, you need a lot of water. Some of that water will evaporate and go away, but the efficiency is much higher. It can go up to 60% now. And with even higher values when the steam is used for heating, fuel is usually natural gas in these systems. So if you have a city that you can use, instead of just using condensers to cool the water and lose the 36%, you can direct it to the homes and heat the homes. One thing that is very beneficial, and I've been in a couple of these type of power plants, is between these two, the exhaust gas, you have control over it. So if you want to cut back on power, the only thing you need to do is just to exhaust this gas outwards. So don't direct it to the, steam recovery system. Just exhaust it, and then you suddenly cut your power generation in half. Okay. So with the easy, switch of a switch, you can, just exhaust that heat outwards and shut down the second generator, okay, which sometimes is beneficial when you have a lot of excess power. So easy to control. But again, it's double the equipment. It's going to be much more expensive. That's the reason we use them for mid-load or base load systems. Now, generator cost curves. So in this section, we get into the heart of economic dispatch, the cost models for generators. The generator costs are typically represented using up to 4 different curves, and we will walk through each of them. First, the input-output curve, or I/O curve. This plots the fuel input, the MBTU per hour, which is the heat generated per hour, and versus the net megawatt output. It tells you how much fuel you need to burn to produce given amount of power. Second, we have the fuel cost curve. This is just the I/O curve scaled by the cost of fuel. Instead of fuel inputs in MBTU per hour, it gives you cost in dollars per hour as a function of megawatt output. Third, we have the heat rate curve. This plots the average fuel consumption in MBTU per megawatt hour. Think of it like a miles per gallon for a car. It tells you how efficiently the unit is converting fuel to electricity at each output level. Fourth, we have, and this is the most important for economic dispatch, the incremental cost curve, also called the marginal cost curve. This tells you the additional cost in dollar per megawatt hour of producing 1 more megawatt at any given output level. And before we go further, let me remind you of the unit conversion at the slide, which is in the slide. 1 MBTU is 1 million BTUs. 1 million BTU equals 0.293 megawatt hours, or 3.41 mega BTU equals 1 megawatt hour. You will need these for calculations in the next slide. Now, this slide shows an example of an input-output curve. The x-axis is the net megawatt output of the generator, and the y-axis is the fuel input rate in MBTU, or million BTUs per hour. Notice that the curve is not linear and does not pass through the origin. There is a non-zero fuel input, even at 0 or minimal power output, that you can see. Where did I put? And you can see here. Now, what does this mean? Why is it non-zero, even if we don't have any? We're still burning fuel, but we don't have any output. 0 output, we're still burning fuel. What is this? I'm sorry? Again, louder. Yes. Startup and just to maintain steam pressure. It represents the consumed fuel just to keep the plant running. It's like just to keep everything warmed up, because until the water reaches 100 degrees Celsius, you won't have any power generated, okay? So imagine you have a cold water to 100%, you're not generating any power, but you're still consuming fuel, okay? And it's going to be very inefficient if you do that. And we call this the no load cost as well. This part is the no load cost. It's just keeping it. It's like a car that is idle, running idle. Now, as the output increases, the fuel input increases, but not at the constant rate. You can see that. And it goes from 0 to 200. This goes from about like 100 to, let's say, 1800, something like that. Now, the shape of the curve reflects the thermodynamic efficiency of the unit at different output levels. But in practice, generators have a minimal stable generation level below which they cannot operate stably. They also have a maximum output. So we can only care about the curve between those two limits. Above a certain level, you have limitations on your turbines, on your boiler. It's going to explode if you have too much pressure on it. So again, we operate between that minimal and maximum. And this I/O curve is the foundation that we have from which we derive the other three curves. Now, this one is the fuel cost curve. This is simply the I/O curve multiplied by the cost of fuel. For example, if coal cost is, let's say, 1.7 per MBTU, and it changes daily. Then for any given megawatt output level, you take the fuel input in MBTU per hour from the I/O curve and multiply it by 1.7. Now, the y-axis of the fuel cost curve is dollar per hour. This is the total. Just give me a second. This is the total power operating cost of the generator at given output levels. And we typically approximate this curve with a quadratic function of the form of, I would explain this equation later. CP is going to be A plus BP plus CP squared. And P is the power output. Power output. And we measure it in megawatts. Now, A and B and C are the constants that are determined by fitting the curve to the data. So it's different for any generator. This equation works well for most generators and makes the math of economic dispatch much easier to understand and trace. Now, the heat rate curve is the I/O curve divided by the megawatt output. It gives the average fuel consumption per unit of electrical energy produced in MBTU per megawatt hour. Think of it like the fuel economy in a car. Just as we measure fuel efficiency in miles per gallon, the heat rate measures the fuel efficiency in of the power plant in megawatts per MBTU per hour. Now, a lower heat rate means a more efficient power plant. The heat rate is not constant. It varies with output levels. Now, most generators are most efficient at some intermediate output level, not at their absolute maximum, because at the absolute maximum, you're going to waste a lot of heat. The best modern combined cycle plants have a heat rate of around 6.5 to 7 MBTU per megawatt hour. MBTU per megawatt hour. Sorry, I'm at the corner and I can't. Per megawatt hour. Now, older, smaller units, so this is the best system. The old models are around 10 mega BT, your million BTUs per megawatt hour. Now, the slide we have values for around 9 MBTU per megawatt hour. And this corresponds to a thermal efficiency of about 38%. Since 3.41 MBTU equals 1 megawatt hour. So it's not the best, it's like average to low. So best system, it's going to be actually less or equal to 6, something around here. It means that you put lower power or heat into it and you generate more electricity. Same thing for a car. Imagine that a car that runs goes 1 mile on 2 gallons or 1 mile on 4 gallons. Which one is better? Obviously, the one that runs on just 2 gallons is going to be better. That's a pretty bad situation, but anyway. Okay. Now, this is the incremental or marginal cost curve. This is also called the incremental is also called the marginal cost curve. It's the most important of the four curves that we had for economic dispatch. It plots the incremental cost in dollars per megawatt hour as a function of megawatt output. In other words, it tells you if I want to generate 1 more megawatt, how much will it cost for me? So going for like a 200 megawatt to 210 megawatts. Now, mathematically, incremental cost is the derivative of the fuel cost curve with respect to power output. So if your cost curve is CP of A plus BP plus CP square, if we take a derivative of this, D of CP over dP, what would the answer be? What is the derivative of the upper equation? B plus 2CP. Thank you so much. Which gives you actually the slope that we have here. Now, for a quadratic cost curve, the incremental cost is a linear function of P if you look at it here. This is convenient because it makes the economic dispatch equations easier to solve when you have a linear equation. For economic dispatch, the key principle, which we will derive formally in a few slides, and I think it's slide number 20, is the optimal dispatch, which occurs when all generators have the same incremental cost, and this is equal to the marginal or incremental cost. Now, in real world, generator cost curves are not perfectly smooth. They can have discontinuous and irregular shapes due to physical constraints like valve points in steam turbines. Again, because thermodynamic laws are not completely linear as well. However, for mathematical analysis, we approximate these curves using smooth functions. Two types of approximations are commonly used. First is the quadratic or cubic polynomial functions that already mentioned. Second is the linear functions, where the curve is approximated by a series of straight line segments. In this course, we will use quadratic cost functions. This means the cost of generator is a function of its output Pi, which is, you can see Ci PGI is equal to alpha I plus beta PGI plus lambda P squared GI. This is dollars per hour fuel cost. And the incremental cost is then derivative of that, which is going to be dCi PGI or dPGI, which gives us beta plus 2 lambda PGI, which, as I mentioned, is linear in Pi. These quadratic approximations are accurate enough for most practical purposes and allow us to develop clean analytic solutions, but they are not perfect. They are just, estimations. Now, here we have an example. Let's do this example to make sure that we understand the unit conversions and the relationship between efficiency, fuel consumptions, and costs. Now, in this example, we have a 500 megawatt generator, which has an efficiency of 35%. It is being supplied Western grade coal, which costs $1.7 per MBTU and has 9,000 BTU per pound. What is the coal usage in pounds per hour? What is the cost? So at an efficiency of 35%, the required fuel input per hour would be 500 megawatt hour over hour times 0.35, which is the efficiency. It's going to be 1428 megawatt hour over the hour times 1 MBTU over 0.29 megawatt hour, which is going to be 4,924 MBTU over hour. Now, where did we get that? We convert MBTU per hour, which is 1,428.6 times 28 times 3.41, which gives us 4,872. And divided by 12.29, we get that. Now, 4,924 times 1 over 0.009, which is because it has a 9,000 BTU per pound, it gives us 547,100. In other words, it's around 200, and if you divide it by 2 almost, it's going to be around 271 metric tons of coal per hour. So around 271 metric tons. Now the cost is going to be equal to 4,924 hour times $1.7, which is going to be $8,370 per hour, or $16.74 per megawatt hour. Now, in other words, running this plant for 1 hour, how much would it cost? It will cost around $8,300 just in fuel. Okay? Keep in mind, this is just in fuel. We don't put maintenance, capex, anything else. This is just for the fuel. Now we can see that economic dispatch matters. Even small improvements in efficiency across many generators translates to a significant saving down the line. Now, this is another example. We want to trace the coil consumption all the way back from a simple household item. We have a 100-watt light bulb left on by mistake for 8 hours, and that the electricity is supplied by the previous coal plant, and that transmission and distribution losses are 20%. How coal has been used. So with a 20% loss, 100% load on for 8 hours requires 1 kilowatt of energy. Because 8 hours is going to 800 watts, and you have the 20% off top of that, so it's going to be around 1 kilowatt. With a 35% generation efficiency, this requires 1 kilowatt over 30.35 times 1 megawatt hours over 1,000 kilowatt hours times 1 MBTU over 0.29 megawatt hours times 1 pound over 0.009 MBTU, which gives us 1.09 pound of coal. So leaving it on the 100-watt bulb on for 8 hours burns about 1 pound of coal. Now, this kind of end-to-end analysis helps us understand the real impact of electricity consumption and reinforces why efficiency matters at every stage of power system. So if you replace this 100 bulb with a 20-watt LED light, instead of consuming 1 pound, you're consuming 0.2 pounds of. So it makes a huge difference. So imagine you have 100 of these light bulbs, and imagine the carbon footprint. So now the coal is mined in northeast. It must be shipped with a train. So imagine how much in the total supply chain you're gonna save. Now, this is an incremental cost example. Let's work through this example using actual cost function parameters. So for 2 generator systems, we assume that C1 PG1 is going to be 1,000 plus 20 PG1 plus 0.01 PG1 square. And for C2, it's going to be 400 plus 15 PG2 plus 0.03 PG2 square, both of them in dollars per hour. Then we want to find the derivative, because we want to find if we add 1 megawatt, how much. So we have to find the slope to predict the extra power. And we get to 20 plus 0.02 PG1. And for PG2, IC2 is going to be 15 plus 0.06 PG2. Both of them in dollars per megawatt hour. Now, if PG1 is 250 megawatts and PG2 is 150 megawatts, then C1 of 250 is going to be $6,625 per hour. And for C2, it's going to be $6,025 per hour. So then IC1 is going to be $25 per megawatt hour, and IC2 is going to be 24 megawatts per hour. So you can see that system number 2, if you want to add 1 megawatt, each megawatt will cost you 24. For system number 1, it's going to cost you 25. So you can notice here the incremental costs increase with the output. Now this reflects the physics. As you push a generator to its limits, you are operating it less efficiently, and each additional megawatt becomes more expensive to produce. And this increase in marginal cost is what makes economic dispatch meaningful. Now, different generators have different cost characteristics as well. So it's not like all of them have the same, equation. And we need to know that to minimize the additional cost. Let me see, how many slides do we have left? Now, now we want to formally define the economic dispatch problem and find the formulation for it. The goal here is to minimize the total instantaneous operating costs of all generators, subject to the constraint that the total generation equals the total load plus losses. Now, mathematically, we will minimize the sum of CI, PI for all generators, I, subject to the constraints that the sum of PI equals PD plus losses, where PD is the total demand. So PD is our total demand. And P loss is obviously our loss. Now, the first thing that we want to do is we want to ignore all the transmission losses. This is what we call lossless or copper plate assumption. We assume all generators and all loads are connected at a single bus with no losses. That's the reason we didn't put transmission losses here. Now, second thing we want to do, we will initially ignore the generator's megawatt limits, the minimal and maximal output constraints. These back in later, so we would ignore that. And with this simplification, the problem becomes to minimize the total cost, subject to equality constraints that total generation equals total load. This is a constraint optimization problem. And we want to solve this through a method that we call Lagrange multipliers. I think you're already familiar with this from control systems. Okay, I think it's enough for today up to this point. We will continue with it next Monday, because if I start this, I have to go through some examples for this. Next week, I will solve some practice problems on this topic. And I think next week is the last week of the class, yes? So we're going to finish this topic, and I will start with a review session for your final exam as well. I would allocate, I think, the Wednesday. Monday, we will finish this. This is going to set last slide, economic dispatch. And on Wednesday, we will start with a review session for the final exam. Thank you so much, and I'll see you next week.